Hi everyone. In this lesson we're going to go over the integral and p-series test to determine convergence or divergence for infinite series. Now once again, these tests will only determine if your series converges or diverges. It will not tell you if your series converges exactly what it converges to. So first of all, let's consider the integral test. So it makes this statement: if you have a function f of x, which is a positive decreasing function for x greater than or equal to 1, and f of n, f evaluated at integer values, equals an, which is your sequence that you're going to be considering, then we have the following result. The summation from 1 to infinity of the an's converges if and only if the integral from 1 to infinity of the function f of x converges. Now the way you should interpret this if and only if, you should interpret it as being if the series converges, then the integral converges, and if the integral converges, then the series converges. So there's really two if-then statements going on there. Now another way to interpret it is quite simply like this. Both the series and the integral do the same thing. If one of them converges, the other one must converge. Or if one of them diverges, then the other one must diverge as well. So that's another way to interpret it. They both do exactly the same thing, as long as the f of x satisfies the necessary conditions, that it is a positive decreasing function and f evaluated at the integers equals your an sequence. And let's take note of one other thing. The requirement that f of x be a positive decreasing function for all x bigger than or equal to 1 can actually be relaxed a little bit. All you actually need is that f of x is a positive decreasing function for x greater than or equal to some fixed value n. So it doesn't necessarily have to be for x bigger than or equal to 1, just for x bigger than or equal to some fixed value n. For example, for x bigger than 1,000 or 10,000, this has to be true. That's all you really need. Now we'll look at the proof of this later on, but first let's look at a few examples. Now with our first example here, we want to determine if the series from 1 to infinity of 1 over n squared plus 1 converges or diverges. So to use the integral test, our function f of x that we're going to use is simply going to be 1 over x squared plus 1. So all we do is replace the n with an x. That's all we do. So that's our function. Now we do need to verify that it satisfies the conditions of the integral test. So first of all, note that this is definitely a positive function for x bigger than or equal to 1. That's certainly true because x squared is always positive, x squared plus 1 is always positive, so yes, this is a positive function. Now we need to verify that it's decreasing. Well, if you think back to the first derivative test from Calculus 1, a function is increasing where its first derivative is positive and decreasing where its first derivative is negative. So we need to verify that the derivative of this function is negative. Then that will mean the original function is decreasing, and that's what we want to verify. Well, if we take the derivative of this function, you can verify that using the quotient rule. You'll get this. So this is the derivative using the quotient rule, or you could use the chain rule if you want to think of this as being x squared plus 1 to the negative 1 power. You could use the chain rule here and you'll get this. Well, notice that the derivative then is certainly going to be negative for x bigger than or equal to 1, right? This is certainly a negative value because of this negative right here. So therefore, f of x is positive and it is decreasing for x bigger than or equal to 1. So the conditions of the integral test are satisfied. So now what we need to do is evaluate the integral from 1 to infinity of f of x dx. So we'll evaluate this. If this exists, then our series will exist or converge. If this does not exist, then our series will diverge. So let's evaluate this and see what we get. Well, remember, this is an improper integral, so remember technically what we do here is we replace the infinity with the b, and then take the limit as b goes to infinity. Now, to evaluate this integral right here, we need to find the antiderivative of 1 over x squared plus 1. Well, that's a familiar function. The antiderivative of this is just the arctangent function, right? So, okay, we evaluate the arctangent from 1 to b. So we put the b in there. There it is. Put the 1 in there for x. There it is. We subtract, and we take the limit as b goes to infinity. Now you have to remember for the arctangent function, the limit as b goes to infinity of this term, limit as b goes to infinity of the arctangent of b, that's going to be pi over 2. So this term right here is converging to pi over 2. And if you forgot about that, remember the graph of the arctangent, if you were to graph it, it has a horizontal asymptote at positive pi over 2, right? Okay, so if this is pi over 2 right here, your arctangent function, remember, looks like this. So as x goes to infinity, the arctangent of x approaches pi over 2. And as x approaches negative infinity, it will approach negative pi over 2. Okay, so remember that from the graph of the arctangent. Now the arctangent of 1, well, that's pi over 4. And so if we take the limit as b goes to infinity of this quantity, we get pi over 2 minus pi over 4, which of course is pi over 4, and that exists as a number. So therefore this improper integral exists, and so therefore the original series exists or converges as well. And there you go. That's how we use the integral test. And before we leave this example, let me point out just one shortcut. When you evaluate this improper integral, you could avoid using the limit as b goes to infinity as long as you understand that the arctangent of infinity should be thought of as pi over 2. So, for example, if you wanted to evaluate this, you could say that that is equal to the arctangent of x evaluated from 1 to infinity, which you could write as like that. Now, as long as you understand that this really means the limit as b goes to infinity of the arctan of b, you can interpret the arctan of infinity as being pi over 2, and this is pi over 4. And there's a little shortcut you can do, like that. Now let's take a look at another example. Now in this example, we want to determine if the series from 2 to infinity of 1 over n times the natural log of n converges or diverges. Now you notice we started at 2 with this series because the natural log of 1 is 0, so we don't want to divide by 0. So to use the integral test, our function f of x that we'll use is going to be this. So all we do is simply replace the n's with x's, and that's going to be the function that we use. Now we need to verify that that function is positive and decreasing for x bigger than or equal to 2. Well, let's notice that certainly this function is positive for x bigger than or equal to 2 because x is positive. The natural log is positive for x bigger than 1, so yes, this will be a positive function. Now we have to verify that it's decreasing. So to do that, we'll verify that the derivative is negative. Now the derivative of this function is going to be what we have written over here. So it's going to be negative 1 over x squared times the ln of x minus 1 over x squared times the natural log of x, and that whole thing squared. Now to verify that this is our derivative, you could just use the quotient rule here. So if we take the derivative of this using the quotient rule, we get bottom times derivative of the top. Well, derivative of 1 is just 0, so we get 0 minus 1 times the derivative of x ln x. Well, we have to use the product rule there, so that's going to be x times the derivative of ln x is 1 over x minus ln x times the derivative of x. And then we divide by the bottom squared. Okay, so there's our f prime. And then simplifying this a little bit, notice that this quantity is 1. And so what we get is negative 1 minus and then breaking that fraction apart, we get and ln x over this is going to give us 1 over x squared times just a single ln of x. And there you go. That's how we get this up here. Now, notice that this, of course, is negative, right? Negative 1 over x squared times ln x. Well, just note that the denominator is always positive here, right, for x bigger than or equal to 2. The denominator over here is also positive for x bigger than or equal to 2. And since we have two negatives up here, this is going to be less than 0 for x bigger than or equal to 2. Okay, so that means that this function is a decreasing function for x bigger than or equal to 2. So we can use the integral test. So now what we do over here is we evaluate the integral of the function from 2 to infinity, and we'll see if this exists or not. Okay, so remember we need to replace the infinity with a b. Right there it is. Take the limit as b goes to infinity. And let's see, evaluating this definite integral right here. So we have to evaluate that. Now remember what we do here with this. Let's just do that off to the side here. Okay, so the antiderivative of 1 over x times ln x. Little substitution problem here. U is going to be the ln of x. So du is 1 over x dx. And we get here, now the dx over x, that becomes du. Ln x becomes u. And of course this is the ln of the absolute value u plus c, but u is ln x. And there you go. There is our antiderivative. Okay, so going back over here, the definite integral from 2 to b. All right, so this is going to be the ln of the ln of x evaluated from 2 to b. All right. Now we put the b in for the x, the 2 in for the x, and subtract. And that's what we get right here. All right. Now, in the limit as b approaches infinity, the natural log of b, and there should be a b right in there. This x right here should be a b right there. As b goes to infinity, the natural log of b goes to infinity. So what's inside here goes to infinity. And then the ln of that quantity is also going to be infinity, because the limit as x approaches infinity of the ln of x, right? Remember, that is infinity because the natural log, if you look at its graph, it goes to infinity, right? Let me just graph the natural logarithm function for you here. Remember this. The graph of the ln of x looks like this, right? Keeps going all the way up to infinity as x goes to infinity. So certainly this is true. So since the ln of b is going to infinity, the ln of the ln of b will also be going to infinity. So this piece right here is approaching infinity. Right there it is. This is just the natural log of the natural log of 2, whatever it is. It's just a number. There it is. So infinity minus a number is infinity. Okay, so this integral does not exist. Okay, and so we see then by the integral test, since this integral diverges, the original series up here diverges as well, so it does not exist. And there you go. That's how you use the integral test for this example. And let me just point out one little shortcut here in evaluating this integral again. Just like the previous problem where we saw with the arctangent, you could state that the integral from 2 to infinity of... Alright, so once you understand that the antiderivative of this is the natural log of the natural log, you could say that this is the ln, absolute value ln of x, evaluated from 2 to infinity. And just taking a little shortcut here, you could write this as like that. Now, as long as you understand that the ln of infinity, this means the limit as b goes to infinity of the ln of b. This is going to be infinity. So you get the ln of infinity minus the ln of the ln of 2. Now the ln of infinity again, well, that should be thought of as the limit as b goes to infinity of the natural log of b. Well, that's also infinity minus, and then this is just going to be a number. And you get infinity. So just a little way of thinking about it without putting the b's in there. You really are putting the b's in here when you're doing this because you're thinking of the ln of infinity as being the ln of b and then letting b go to infinity. But it's just a shortcut here. Now let's take a look at this theorem. This is called our p-series test. This is an important result since we'll use it a lot when we study the domination test and the limit comparison test. So the theorem makes this statement. This series, the sum from 1 to infinity of 1 over n to the p power, it will converge for p bigger than 1 and diverge for p less than or equal to 1. So for example, if we look at the summation 1 over n cubed from 1 to infinity, in this case the p is equal to 3, so The theorem simply tells us that this will converge. So it converges. If we look at the summation from 1 to infinity of 1 over the square root of n, well, in this case, the p is 1/2. Well, 1/2 is less than or equal to 1, so this series diverges. If we look at the summation from 1 to infinity of, say, 1 plus n divided by n to the 4th power, well, we can use this test also because we can write this as like that, and then we can break that up as like that. Now in this one right here, the p is 4, so since p is bigger than 1, this will converge, and over here the p is equal to 3, so this will converge as well. So therefore our original series, like this, will converge. And there you go. So those are 3 quick examples how you use the p-series test. So this is a very important result. Now the proof is actually very easy. Let's take a look at it. So it's pretty simple. All we need to do is to note that by the p-integral test, which we studied back in section 8.7 when we were studying improper integrals, this improper integral, the integral from 1 to infinity of 1 over x to the p, that converges for p bigger than 1 and diverges for p less than or equal to 1. Remember, we had that result. So therefore, by the integral test, since the summation and this integral will do the exact same thing, we then have that the summation of 1 over n to the p power will converge for p greater than 1, and it will diverge for p less than or equal to 1. And that's it. That's all you have to do, is invoke the p-integral test and the integral test for series, which is theorem 9.3.1 that we had looked at previously. Now let's take a look at the proof of the integral test. We didn't prove that, so let's go over the proof of that down here. Now the proof of the integral test is a very interesting proof because we're going to use a diagram to help us to prove this theorem. And if we look at that diagram in 2 different ways, the same diagram in 2 different ways, we'll draw 2 different conclusions. They're not in conflict with each other, but just 2 different conclusions to help us prove this result. So here's how the proof goes. So we assume that the conditions of the integral test are satisfied. We have a function f of x that is positive, decreasing for x bigger than or equal to 1, and also that f of n equals an. Now, to show that the summation converges, if and only if the integral converges, you must do 2 things. Now keep in mind that when we make this statement, if and only if, we're really making 2 statements. We're really saying if this is true, then this converges. And if this is true, then the series converges. So it really consists of 2 different statements, 2 if-then statements. That's what an if and only if means. So we need to prove 2 things here. We need to prove that if the series converges, then the integral converges. And if the integral converges, then the series converges. So we actually need to prove these 2 things separately in order to conclude the if and only if statement is true. Now we're going to use just a little trick here. Instead of proving these 2 statements directly, it's just a little bit easier if we prove their contrapositive. Now we could prove these directly, but using the contrapositive is just a little bit easier. So the contrapositive of these two statements are as follows. So for the first one, if the series converges, then the integral converges. The contrapositive of that statement is that if the integral diverges, does not converge, then the series diverges, does not converge. Okay, so the contrapositive goes in this direction, and we negate the B and the A. Okay, now the contrapositive of the second statement is that if the series diverges, then the integral diverges, right? That's down here. Okay, so these two statements are the same as these two statements. And these two statements combined tell you that the series converges if and only if the integral converges. Okay, that's actually comprised of two separate if-then statements, one going in this direction and the other going in that direction. Okay, now let's prove these two statements down here. So let's prove these two. Okay, so to prove number one, we're going to look at this diagram. So we want to prove this statement first, that if the integral diverges, then the series must diverge. Okay, so here we have the diagram of a function that is decreasing and positive. Now, if you look at the area of these circumscribed rectangles, take a look at this rectangle right here. So right here, this height right here is f of 1. Now that's the same as a1, right? Because a1 is supposed to equal f of 1. Okay, so the area of this rectangle right here, well, that's just going to be its height times its width, but its width is 1. So we actually have that the area of this rectangle is a1. That's the area, okay? Because the width is 1. So a1 times 1, that's the area of the first rectangle. The area of the second rectangle right here is going to be a2. The height is a2, or f of 2, and the width is 1 again. This rectangle a3. And all the way down, and this rectangle right here is going to have area A. If that's the point n minus 1 on the x-axis, this is going to have area A n minus 1. Okay, so let's interpret the nth partial sum then, right here, actually the n minus first partial sum. That's what we have right here, as actually being the area of all of these rectangles added together. Now from this picture, you see then that the area of all of these rectangles added together, which is what we have right here, that's the area of all those rectangles added together, is greater than the area underneath the graph of the function from 1 to n. So you see it's bigger than or equal to the integral from 1 to n of f of x dx. Okay. Now, we assume that the integral from 1 to infinity of f of x diverges. So that means that the limit as n goes to infinity of the integral from 1 to n of f of x dx is equal to infinity. That's by assumption. Okay. However, the n minus first partial sums are bigger than all of these areas, and these go to infinity. So therefore, we see that the limit as n goes to infinity of the summation from 1 to n, technically you should put an n minus 1 here because we had an n minus 1 here. Well, that's going to be infinity. And so therefore, the summation from 1 to infinity of a sub n diverges. And there you go. It's all just because of the way you look at the area of these rectangles. Okay, so that was a pretty neat little proof. Now let's take a look at the proof of part 2. Now all we have to do is look at this picture a little differently, and we'll be able to conclude part 2 is true as well. All right, now for part 2, remember that's up here. We want to show that if the summation diverges, then the integral diverges. Okay, so that's what we want to prove for part 2. Now, same diagram, but now what we're going to do is we're going to draw our rectangles so they're actually inscribed under the graph instead of over top of the graph. This is a pretty neat trick here. So look at this first rectangle that we have here. Remember before, the way we drew this rectangle was we drew it over top of the graph, right? We drew them over top of the graph. Well, now we're going to draw them underneath it. Okay, so this first rectangle that we have labeled here is actually A2, because you see the height is A2, that's f of 2 right there, that height is f of 2, and the width is 1, so this area is A2. This rectangle, the area is A3. This rectangle here, the area is A4, and so on. This rectangle down here has area AN. So now we see that the area of all these rectangles added together is right here, the sum from 2 to n of AK. Now that's going to be less than or equal to the integral from 1 to n of f of x dx, right? That's going to be less than the area underneath the graph of the function, because the rectangles are now inscribed underneath the function. Now we're assuming that the series diverges, so that means that the limit as n goes to infinity of your summation from 2 to n of AK is equal to infinity, because it's supposed to diverge. And so we see then that the limit as n goes to infinity of the integral from 1 to n of f of x dx must also equal infinity, because it's actually bigger than these terms are. And these terms go to infinity that we have circled here, so therefore the limit as n goes to infinity of this term must be infinity, and so therefore your integral diverges. And there you go, we just proved part 2. And that's it. And that's how we prove the integral test. That's a really slick proof, because depending on how we drew our rectangles, whether they were over top or underneath the graph, we could conclude 2 different parts of our proof. And that concludes this lesson on the integral and p-series test.